All right. Today, I'm going to be talking a little bit about the synthesis of carboxylic acids as well as carboxylic acid derivatives. So just for a quick intro, carboxylic acids are a functional group, or they make up a functional group, which is characterized by a carbon double bonded to an oxygen and then also bonded to an alcohol group. So there are obviously many different carboxylic acids, and any number of these functional groups can be contained in a particular molecule. But these different types of carboxylic acids are incredibly versatile. Primarily, they are more acidic than other organic groups that contain hydroxyl groups, but they are weaker acids than like hydrochloric acid or different acids that we think of when we typically think acid. They are also extremely common in the human body. They're a big component of fatty acids. They also are present in lactic acid, citric acid, different things. And then importantly, they are made up, so they are parts of amino acids, which make up all the proteins in our bodies. So, and then over here on the right, we can see all the different types of carboxylic acid derivatives. So we have acid anhydrides, which are characterized by that kind of ester in the middle. And then acid chlorides, which is like a carbonyl group bonded to a chloride. Amides, which have that nitrogen bonded to an R group, kind of in an esteric fashion. And then nitriles and esters down here. So to begin today, I'll start talking about the synthesis of carboxylic acid itself. So this is fairly simple. The nice thing about the synthesis of carboxylic acid is that, So carboxylic acid can be synthesized from each of its different derivatives. So we'll start with an ester here, and then, sorry about that. So if you take an ester plus an acid and water, what happens is the hydrolysis of carboxylic acid. And I'll go ahead and show the mechanism for this down below because it happens the same way for esters, acid anhydrides, and acid chlorides. Obviously, the products are a little different. With esters, you'll have a carboxylic acid plus, depending on the type of ester, an alcohol. And acid anhydrides will result in two equivalents of carboxylic acid, and acid chlorides will give you a carboxylic acid plus hydrochloric acid. I'll go ahead and write out the mechanism for the synthesis of carboxylic acid from esters. So now that we have the mechanism all drawn out for the hydrolysis of esters to form carboxylic acids, we'll walk through the mechanism quickly. So first step here is the protonation of the oxygen atom at the top of that ester. So it's going to seek out that hydrogen, and then the hydrogen will leave the H3O plus that is in solution, which is our acid in this scenario. And then the next step of this mechanism is a nucleophilic addition of a water molecule. And you can see that that water molecule adds to that alpha or that carbon that's directly connected to the oxygen. And then after that, this one looks a little bit confusing, but basically what happens is that we have a proton transfer from this water molecule here. So we're transferring the protons from the oxygen to that hydrogen and then to the oxygen again, which causes the hydrogen to leave and leaves us with an alcohol functional group in its place. And that also regenerates the H3O plus in solution, which in the next step allows for another proton transfer, this time from that. You can see how we had the kind of the remainder of the ester here with the oxygen bonded to the ethyl group. So then in the second proton transfer, we're actually protonating that oxygen, which eventually causes the O, so it's an ethanol that ends up leaving. So then the last step after the elimination of ethanol is the reprotonation or the deprotonation, excuse me, of that oxygen atom at the top of the molecule, which leaves us with a carboxylic acid here. And in this particular case, ethanol. So a very similar mechanism happens for the hydrolysis of acid anhydrides as well as acid chlorides, because these are both acid catalyzed hydrolyses, which result in carboxylic acids. Okay, now I'll go ahead and draw out a mechanism for one of the base catalyzed mechanisms, and then we'll move on from there. So as we can see, for the base catalyzed hydrolyses that result in carboxylic acids, I went ahead and drew out what that would look like using a secondary amine here, or amide, excuse me. So first step we can see is the nucleophilic addition of that hydroxy group, and the subsequent breakage of that double bond that is bonding the oxygen to the carbon. So now we're left with a highly electronegative oxygen that's single bonded to the carbon, an OH group, and then we still have that amine group over here. So those electrons from the oxygen come back down and end up kicking off that amine group, and we are left with that carboxylic acid. So that one's quite simple. I've kind of organized what the different hydrolyses of carboxylic acid derivatives look like. So over here are our acid catalyzed reactions. And so here's the esters hydrolysis that we went through. Here's an acid anhydride one and an acid chloride. Over here is the nitrile, and then of course that amide that we just went through. Now you can see that I've gone ahead and drawn out the reactions for 3 other ways to synthesize carboxylic acids. So the first method of synthesis is through oxidation of a primary alcohol. So as we can see here, we have ethanol, and then our oxidizing agent and H2SO4, which does result in carboxylic acid. All of the mechanisms for these have been previously discussed in organic chemistry, so I'm not going to go into too much detail on those. So the second one is ozonolysis, which, like I mentioned, we've gone into detail on before. So you're going to have your trioxide and your H2O2, and that ozonolysis reaction often results in that double bonded oxygen on 2 split molecules. And so one of those molecules is a carboxylic acid. And then finally, and possibly most effectively, is your Grignard reaction with carbon dioxide. So as you can see here, you start with a benzene ring which has been halogenated with bromine, introduce magnesium and ether, which results in the addition of magnesium to that molecule, and then add CO2, which essentially adds your carbonyl group, and then finally the addition of H3O plus protonates that oxygen and leaves you with a carboxylic acid. There are many different ways to synthesize the derivatives of carboxylic acids from carboxylic acid. So I thought that it would be easiest to just go ahead and draw them all out in a reaction circle and then walk through each one in a little more detail. So we'll start up here where I'm drawing. And as you can see, we have the reagents being H2SO4 and basically any kind of alcohol. And so this results in a process known as Fischer esterification, which just refers to the formation of an ester from a carboxylic acid using those particular reagents. And then to the right of that and kind of down the circle, we see CH2N2 as a reagent. And this is a different way of forming carboxylic acids, forming esters from carboxylic acids. Moving on, we have SOCl2 and then CH3I. And this is yet another way to form carboxylic or to form esters from carboxylic acids. This in particular being a methyl ester. And then the next synthesis is for anhydrides. So oddly enough, you can form anhydrides with just two equivalents of a carboxylic acid and heat in combination, which is quite the simple reaction, but very useful. And then alternatively, you can use 1/2 an equivalent of a carboxylic acid plus SOCl2, and you will also end up with an anhydride. The next one is just a ketone. And so that can be formed using two equivalents of an organolithium reagent and an acid. And then we have acid chlorides, which can be formed with SOCl2. So notice the similarities with that and esters, except with esters, you just take it a step further with the CH3I. And then over here we have amide formations. So down here is a primary amide, and up here's a second, or also a primary amide. So you can also go with this SOCl2 up here, but then you do have to add basically an amine. And here you can do an amine and heat. So SOCl2 is a very versatile reagent in this situation, and it is good to note that carboxylic acids are pretty reactive. So in a lot of these, you only need fairly mild reagents or heat. So fairly environmentally friendly goes along with a lot of those principles of green chemistry. And then up here is our last one, and that would be the formation of a secondary amide, which is a little bit hard to see, but that's a second R down there, just representing another functional group. But for this one, we would use DCC and then another, any kind of amine. So anyway, the synthesis of all these different carboxylic acid derivatives is very necessary, as each of these are very versatile. So the synthesis of each of these different carboxylic acid derivatives is very important to look at, because all of these derivatives are used in the production of different polymers, biopolymers, coatings, adhesives, pharmaceutical drugs, solvents, food additives, antimicrobial flavorings, and many other different products that we use in day-to-day life.